In this video, we will remember how we can draw the Root-Locus for an arbitrary parameter in the closed-loop structure. Okay, so normally what we have is we have a like g of c or g all of c, okay, open loop transfer function, and we have a constant gain k, and we draw the Root-Locus with respect to k. But the problem is the structure doesn't have to be in the standard form. Maybe we are drawing Root-Locus with respect to pi gain, d gain, or some other parameter. Okay, so for example, in this case, okay, we have a first order FIR low pass filter which has a constant parameter a, and we would like to understand the behavior of the roots or the closed pole locations with a varying parameter of a, and we know that a is greater than or equal to 0. Okay, so how we can do that? So what we should do is we should somehow transform it into standard form. Let's remember that we technically draw the Root-Locus with respect to the equation of this 1 plus k times GOL of z is equal to 0. Okay, so if we can write an equation such that 1 plus a times some transfer function, let's say g bar of z is equal to 0, if we can do that, and then we can draw the Root-Locus with respect to g bar, which will be technically the Root-Locus diagram with respect to parameter a for the original closed-loop system. Okay, let's analyze it and try to figure out what we should do in the specific example. Okay, so y of z divided by r of z is equal to, if we analyze that, okay, 0.25 plus a times z to the power minus 1 g of z divided by 1 plus 0.25 plus a times z to the power minus 1, okay, g of z. Okay, so what is the equation that we use to computing the roots? It is this. Okay, so technically this is our original equation. 0.25 plus a times z to the power minus 1 times g of z is equal to 0. So what we do is, since a is the parameter that we are interested in, we group everything with respect to multiply with a and not multiply with a. So our first part is equal to 1 plus, okay, 0.25 g of z, and the other part is equal to a times g of z divided by z minus 1 equal to 0. Okay, that's good. So we are just getting somewhere else. So if I divide both parts with this, okay, 1 plus 0.25 times g of z, what we will obtain is this, 1 plus a times, okay, z to the power minus 1 g of z divided by 1 plus 0.25 times g of z is equal to 0. Now we convert it into a standard form, and let's call this part, okay, g bar of c, and if we draw the Root-Locus with respect to g bar of c, then we technically draw the Root-Locus diagram with respect to a. Okay, that's good. So let's solve an example. Okay, and it is given that g of z is equal to 1 over z minus 1. Okay, so g bar of z is equal to, if you remember, okay, so 1 over z times g of z divided by 1 plus 1 over 4 or 0.25 g of z. That's good. So g of z is given as this, and in this case it's equal to 1 over z squared z minus 1 divided by, okay, 1 plus 1 over 4, okay, that is equal to 1 over z times z minus 1. Okay, so if I combine everything, it will be equal to 1 divided by z times z squared plus minus c plus 0.25, or let's call it 1 over 4, which is easier for us. Okay, it's very good. So as you can see, this modified open transfer function has 3 poles. Okay, so one pole is at the origin, and we have a repeated pole at, I guess, 0.5. That's good. Okay, so this is our unit circle. Let's draw it like this. So if we draw that, we can see that this part, let's make it very thick, is on Root-Locus. Okay, it's going down that, and we have asymptotes, and since we have 3 poles, asymptotes are like 120 degrees apart from each other. It will be something like this, and I think it will be something like that. Okay, so as you can see, the system in respect to A starts stable, okay, which is an expected result. And if we, as we change A, make it bigger and bigger, it becomes more unstable, and at some point it breaks stability. Let's look at the MATLAB plot. As you can see, it is very similar, okay. So if you compute the intercept is somewhere here, okay. It's also possible to compute that, which is very easy using the formula. And when A is equal to 0.5, which is like 2 times the 1 over 4, it becomes unstable. Okay, so this is a nice result. I really like it because this is a low pass filter. And as we increase A, especially until some point, it will become more and more low pass. So we are changing technically cutoff frequency. So as you can see, it's maybe unexpected for some of you. So adding a low pass effect is not affecting stability in a positive manner. It's kind of degrading the stability. The system is reached its stability limit in terms of like best performance when A is equal to 0. As we increase it, it will become more and more unstable, and at some point it will be unstable. It can break unstability point from here or here, but in this case, A is 0.5 when the Root-Locus technically crosses the unit circle. Okay, so in general, in the midterms and mini projects, we may want you to draw Root-Locus with respect to an arbitrary parameter, and this is how you need to approach the problem.